Hello everyone. Today we discuss continuous functions on intervals. The goal is to prove the Bolzano intermediate value theorem, which says the following. Let I be an interval and let f be a function from the interval I to the set of real number R, and assume that this function is continuous. If A, B are points in this interval I and K a real number satisfies f of A smaller than K smaller than f of B, then there exists a point C in I such that f of C must be equal to K. So this is the mathematics of drawing a line on a piece of paper without taking the pencil out of the paper. We have continuous function, thinking about it as represented by a curve, a continuous curve. In order to draw this continuous curve, we have to go from one point to another. The intuitive idea is that because the curve is continuous, we had to draw it without taking the pencil out of the paper. That's why when we go from f of A to f of B, we had to, the function has to assume every value in between. So that is the content of the Bolzano intermediate value theorem. If you explain it to some kindergarten children, they're gonna think that this is obvious. You want to draw a continuous curve, then you cannot take the pencil out of the paper, or you take it out, you had to restart it at the same point that you take it out. In order to prove it rigorously, though, is a totally another matter, and it's a somewhat intricate issue. The reason is that we define limit, sequence, function, and continuity by certain axioms only, and we deduce other statements from the axiom, but nothing else. So that is the rules again. In order to prove this theorem, we have to use all the materials we deduce from the axioms we learned in this class. So towards that goal, we're going to start with the definition. A function f from the set A to R is said to be bounded on A if there exists a constant m bigger than 0 such that the absolute value of f of x is smaller than m for all x in the set A. So boundedness is a very common notion. We talk about the boundedness of a sequence in a previous chapter, and now we talk about the boundedness of a function. They are certainly related to each other because a sequence is just a special function. So it is not surprising to see the following boundedness theorem. Let I be an interval from point A to point B, and f a function from this interval I to a set of real number be continuous. Then the conclusion is that F is bounded on I. Now, this is the second half of this class already. So you are, by this point, should be very familiar with the technique of proving by contradiction. And the proof of this theorem is another example. Suppose that the function f is unbounded. Then for any number n, any natural number n, there is some xn in the set in the interval I such that f of xn is greater than n. This is from the definition of unboundedness. The picture looks as follows. Here we have an interval I, and on this interval we can choose these points xn such that f of xn is greater than n. Now we consider the sequence consisting of these xn. We have each xn inside the interval, that is a smaller than xn smaller than b, which imply that the sequence is bounded. Each element in the sequence is between A and B. That's why the sequence is bounded. Now, by the Bolzano-Weierstrass theorem, which says that every bounded sequence has a convergent subsequence, we can extract a convergent subsequence from this sequence. So let's call this subsequence X prime, consisting of elements denoted by X and K. This sequence converge to some number C belongs to this interval from A to B. Now we consider f of x and k, that is the function f evaluated at each point in this sequence. Since x and k approaching C by the sequential criterion, of continuity, we have that f of x and k here must approaching f of C. That's what continuity is about. It translates a limit from the level of the input to the level of the output. But this implies that the sequence f of x and k here is bounded. A convergent sequence is bounded. On the other hand, by the construction that we did earlier, f of x and k is bigger than nk in absolute value, which is greater than equal to k for any natural integer k. That is a contradiction to the statement that this sequence is bounded. And as long as we reach a contradiction, we know that the initial assumption is false, therefore the opposite is true. So the initial assumption is that F is unbounded. So the opposite is F is bounded. And this is exactly what we want to prove. A consequence of that theorem is the following about maximum and minimum of a function. Let f be a function from the interval from a to b to a set of real numbers, and assume that the function is continuous. Then f has an absolute maximum and an absolute minimum on this interval from a to b. Let me use another color to emphasize this notion. I have an absolute maximum and an absolute minimum on the set of on the interval from a to b. Now the absolute maximum is defined as follows. F is said to have absolute maximum on the set A if there is a point A star in the set A such that f of A star is greater than or equal to f of x for all x in the set A. In other words, f of x star equal to the supremum of the function f of x for x inside the set A, and additionally, x star belongs to a set A. So this is really the distinction between absolute maximum and the supremum concept. The supremum concept, for the supremum concept, the value might not be in the set. But for absolute maximum, we require that x star must be in the set and f of x star equal to the supremum of this set. So here is just an example to recall the notion of the supremum. We consider all negative numbers, then 0, 1, 2, 3 are upper bounds. 0 is the supremum, the least upper bound, but 0 is not in the set A. We can define the absolute minimum in a similar manner. Using, instead of the supremum, we use infimum. Now the next theorem will be important to prove the Bolzano intermediate value theorem. It's called the location of root theorem or the bisection method. Let f be a function from the interval a to b to the set of real numbers and assume that the function is continuous. If f of a smaller than 0, smaller than f of b, then there exists a number c inside this interval AB such that f of C is equal to 0. The idea of the proof is follow. We're gonna call an interval a good candidate if the evaluation of the function f at the endpoints of this interval are of opposite sides. And the reason it's good candidate because it has the same property as the original interval here. The key assumption here is that the function assume values of opposite sides at endpoints of this interval. So the idea of this proof is that we're gonna keep breaking down this interval into two equal halves. At each step, we're gonna keep the good candidate and throw away the other one. And the process is stopped if we arrive at a point where the function is equal to 0. And if we arrive at that point, then we are done. That's the whole purpose of doing this process. If not, then we can repeat this process forever. So repeating the process is either yield some point C such that f of C equal to 0, or we have infinite sequence of nested interval. Now, by a theorem in section 2.1, this infinite sequence of nested intervals has a common point x, which belongs to the intersection of all these intervals. The claim is that f of x equal to 0, and we can prove this claim in a rigorous way. But the intuitive idea is that the reason we can continue this process forever because at each step the interval always has endpoints at which the function assume values of opposite sides. So no 0. So being 0 is the condition. Being not equal to 0 is the condition to take this process forever, infinitely many times. That's why the common point in all the intervals must be related to that special condition. And that's why the common point here, as a common point, f of x must be equal to 0. And that is the idea of the proof. Let me give you an example to illustrate how it works. Let's consider the function f of x equal to x times e to the x minus 2. We would like to find value x0 such that f of x0 equal to 0. First of all, we observe that this function is continuous on the set of real numbers. So this is good. Then we observe that f of 0 equal to 0 minus 2 smaller than 0. And f of 1 equal to e minus 2, which is bigger than 0. So by the theorem above, by the bisection method above, we know that the equation f of x equals 0 has some root within this interval from 0 to 1. And how do we find the root? Numerically, we use the bisection method. We keep dividing this interval into 2 equal half. So the first step, we have a0 equal 0, b0 equal 1, and the middle point equal 1 half. So we evaluate the function of this middle point f of 1 half equal to minus 1.176, which is smaller than 0. So the good candidate here is the upper half, the interval from 1 half to 1, because at this at 1 half, f of 1 half is smaller than 0 and f of 1 is bigger than 0. So we throw away the other half, the interval from 0 to 1 half. And we let a1 equal to 1 half, b1 equal to 1. So this is a new interval. And we compute the new middle point, which is 1 half plus 1, which is 3/4. We evaluate the function of this point f of 3/4 equal to minus 0.412, again smaller than 0. So the good candidate is again the upper interval from 3/4 to 1. And we have a2 equal 3/4, b2 equal 1. So let me draw a picture to illustrate what's going on. We have the interval from 0 to 1. And step 1, and let me use some other color here. Step 1, we throw away the lower half from 0 to 1 half, and we keep the upper half from 1 half to 1. Now for step 2, and let me use another color here, we again throw away the lower half and keep the upper one from 3/4 to 1. So this is step 2. And if we repeat this process several times, then we getting closer and closer to the root of the equation. Here, after 7 steps, we already arrive at the conclusion that there is a root between 0.843 and 0.860. So that's a pretty good estimate. And this is actually how numerical calculator give you numerical answer to several equations. So now we can repeat the Bolzano intermediate value theorem and prove it. Again, the theorem says that we have function from the interval a to b to the set of real numbers. Assume it is continuous and f of a smaller than k smaller than f of b. Then there exists a point c within the interval such that f of c equal to k. The proof here actually follows from the location of root theorem in a very natural way. We just consider the function g of x here to be equal f of x minus k. Then the function g of x is going to be negative when x equal a and positive when x equal b. That's why by the location of root theorem, it has a root point c inside interval such that g of c equals 0, and this implies f of c minus k equals 0, which is equivalent to f of c equal to k. And that is the end of the proof. we have several consequences of this important theorem. The first corollary states that we have a continuous function from an interval to a set of real numbers if k is a number satisfying the infimum of this function smaller than k smaller than the supremum of this function, then there exists c inside the interval such that f of c equal to k. Another consequence is about the preservation of intervals. Let I be an interval and f a function from I to a set of real numbers be continuous. Then f of I is an interval. Recall that f of I is the image of the function f, image of the interval I under the function f, which equal to f of x for all x inside the interval I. Furthermore, if I is closed and bounded, then f of I is closed and bounded. So in this section, we discuss a very important theorem for continuous function on an interval. And this is important because it allows us to study not just the continuous function, but the mapping mapping induced by this continuous function. We show that under this continuous function, an interval is mapped to an interval. If the interval is closed and bounded, then its image is also closed and bounded. That's why the theory we discussed in this session allows us to apply real analysis to many problems, including mapping and imaging.